Modern architecture and construction projects demand a massive, continuous flow of precise data. To coordinate intersecting steelwork and orchestrate multiple heavy crane operations, engineering teams must process thousands of technical specifications, plans, and rapid design changes simultaneously. Yet, the industry has historically managed this dense data through linear, asynchronous communication. Stakeholders pass physical paper prints back and forth, or rely on scattered, disjointed email chains to track updates across vast teams. This fragmented approach creates severe bottlenecks. When an architect emails a revised floor plan while a contractor is still working off a printout from 3 days ago, version control collapses, design review cycles become delayed, and teams end up building from outdated specifications. Bluebeam Revu is a software architecture built specifically to eliminate these communication bottlenecks in the AEC industry. It works by redefining the function of a PDF. Rather than treating a digital document as static digital paper, Revu structures the PDF as a dynamic, spatially aware data hub, where information can be actively measured, tracked, and modified. We are going to construct the Bluebeam workflow layer by layer. We'll start with basic file ingestion and standardization, move through spatial calibration, and finish at the highest layer of advanced cloud collaboration. Mastering this environment is about eliminating the asynchronous friction that causes massive schedule overruns and costly on-site rework. The first step in this digital workflow requires bringing disparate file types into a single environment. Complex CAD drawings and standard Office files are funneled down and flattened into a unified, clean 2D PDF format. However, when documents are simply scanned into the system, they often enter as rasterized files. Important technical specifications are trapped as unsearchable images under a pixelated grid, useless to the software. To solve this, optical character recognition sweeps the document. It actively extracts the shapes from the image and translates those trapped pixels into clean, readable vector text. Once the text is digitized, teams bypass the manual process of scanning pages. They can instantly search for specific mechanical components or material keywords across massive, multi-thousand-page document sets. To apply the standardization to the sheer volume of documents in a modern project, the system uses a function called batch processing. Batch processing executes operations on hundreds of files simultaneously. It removes the repetition of converting, standardizing the formatting, and applying OCR to individual sheets. Standardizing and digitizing this base layer transforms a flat, unreadable image into a computable database. The document is now ready to handle advanced engineering tasks. With the text data extracted, the focus shifts to the physical geometry of the design. The software must assign a physical scale to the digital space. Look at this structural floor plan. By drawing a line between two known column grid lines and inputting their actual distance, the user completes the calibration process. This single measurement grounds the entire digital sheet in physical reality. That calibration enables quantity takeoffs. This is the exact extraction of material quantities, lengths, and areas directly from the drawn plans. To calculate square footage, digital polygons are traced over specific architectural zones. Because the document is calibrated, the enclosed areas instantly generate dynamic numerical readouts. For linear measurements, such as perimeter walls or electrical conduit lengths, the tool continuously tracks the distance of the drawn lines, summing them into a running total in real time. Volume calculations are generated by taking those same 2D area polygons and simply inputting the required depth parameters, such as the thickness of a concrete slab. The software also uses digital counting markups. By clicking through the document, a user automatically tallies specific fixtures, doors, or structural joints into a categorized list. These exact figures are then exported seamlessly to feed directly into the models used for precise project cost estimation. Traditional estimators used physical scale rulers on printed paper, a manual process prone to subjective misreads and calculation errors. Digital extraction guarantees mathematical precision, based strictly on the vector geometry. Embedding that spatial geometry directly into the PDF removes the disconnect between the architect's drawn intent and the estimator's final budget. Moving into the quality assurance phase, Teams must review these detailed designs and track necessary changes without losing information in translation. This requires establishing standardized, custom markup toolsets across every engineering and architectural discipline involved in the project. By assigning strict color-coded workflows, the system prevents the misinterpretation of technical notes. The structural team's red lines remain distinct from the civil engineer's grading notes and the architect's finish schedules. When manual reviewers comb through hundreds of revised drawings, they inevitably miss microscopic changes between version 1 and version 2 of a complex schematic. The document comparison tool automates this review. It takes two overlapping blueprint versions and programmatically isolates the geometric discrepancies, highlighting the exact differences with high-contrast red and green clouds. This overlay ensures that subtle omissions, like a shifted load-bearing wall or a removed electrical outlet, are caught before ground is ever broken. Every markup, note, and comparison generates a permanent, trackable digital audit trail attached directly to the file. These QA/QC tools replace the subjective visual check of a design review with an objective, mathematically verifiable system. It secures a digital closeout with zero structural clashes. Pulling back from the single document, we reach the macro-level dynamics of a multidisciplinary project team. This is where Bluebeam's dedicated cloud-based collaboration ecosystem, known as Studio, takes over. The first half of this ecosystem is Studio Projects. As illustrated here, Studio Projects acts as the centralized repository. Disparate project files flow into this single cloud node, managing strict version control and hosting an unlimited number of file types in a unified structure. The second, highly dynamic half of the ecosystem is Studio Sessions. In Studio Sessions, multiple stakeholders open the exact same document simultaneously. Distinctly colored cursors representing different users can add unique measurements, text, and annotations to different quadrants of the drawing in real time. This collapses the old linear sequential review chains. Instead of waiting for the architect to finish a file before passing it to the engineer, the team operates in a highly efficient, concurrent network model. Maximizing this specific collaborative toolkit requires standardized team training. If users do not follow the established folder hierarchy, the shared environment quickly degrades. It also introduces logistical constraints. The software requires licensing fees for full functionality, and users must maintain consistent internet access to keep the live session in sync. Ultimately, the Studio network dismantles asynchronous bottlenecks. It drastically reduces the iteration cycle time and keeps every discipline anchored to a single source of truth. We have built the conceptual stack, converting files into a standard format, applying spatial measurement, deploying QA/QC tracking, and connecting it all through concurrent cloud networking. This completed 2D environment integrates directly with complex building information modeling, or BIM, software. This integration allows users to pull up a complex 3D wireframe model, rotate the physical geometry, and extract exact metadata without leaving the Revu platform. Establishing this digital foundation prepares architecture and construction firms for incoming macro trends of the technology sector. We are rapidly approaching the integration of AI-assisted document review, where algorithms automatically scan these calibrated vectors to detect structural anomalies and verify building code compliance. This structured data will also feed into digital twins. They are living virtual replicas of physical buildings that continually update themselves using real-time sensor data from the fully completed facility. On the ground, the industry is shifting toward mobile-first construction workflows. Field workers are executing these plans by accessing the central data hub directly from tablets on the active job site. Adopting this layered digital architecture provides the foundation required to compete, deliver accurate budgets, and survive in the modern AEC industry.